So we're essentially just doing a quick overview of the things that we've learned so far in CSO. We were introduced to this idea of logic gates, which kind of represent Boolean logic, and we have a few operations here like and, or, not, NAND, which is not and, nor, XOR, and then XNOR. And we'll sort of explain in detail what they are. And of course, we've said that logic gates have different symbols. So depending on the way that it's shaped, it will either be an and or an or an XOR or an and. And among the whole suite of possibilities in terms of logic gates. Um, and so this is how an and logic gate will look. You'll have, you could have two inputs. You could also have one, but let's say you have two inputs here and then you have an output Y. And those inputs are filtered through the logic of and, right? So if you can imagine if A and B were both zero, well, then your Y output would be zero just in truth logic or in truth tables in general, or when you're looking at an and function or a relationship between two things, you're only true when both are true. And so zero in this case represents false. And so if both are false, um, in other words, both are zero, well, then Y is zero. And you can see that if you have any combination of zero and one, right? So you have zero and one, that's zero, one and zero, that's zero. In other words, it's saying if you're false and true, right? Zero and one, that's false. If you're true and false, well, that's false as the whole. And if you're both true, well, then you're true. So and is simply saying that you're true only when both are true. In other words, your output of Y is one when both are one. There's just a quick reminder there to remember that. And here are here are sort of the truth tables for each of the particular cases, right? In the most simplistic sense, you could have a yes, which is essentially just saying, well, whatever the output is, um, it is whatever the input is what the output is, right? So it's zero, well then zero, it's just one. The not, which is denoted by the notch, simply says, well, then you're zero. If you input zero, you'll invert it. If you input one, you'll invert it. So whatever the input is, it will just find out what the complement is, what the inversion of that input is, and it will present it to you. The and here, again, we already spoke about the and. You're true when both are true, and so in this particular case here, 0, 0, 0, 1 and 0 is 0. Again, true and false is false on the whole, and false and true would also be false. You can only be true when both are true. That's the essential idea of and it has this particular shape. The or, when you think about an or just in a general sense, you're true when either or are true or both, right? So in other words, 0 and 0 is 0 because neither are true. 1 and 0 either or, right? So both of these cases are either or. One of them is in fact true, and you result in a true verdict. Here, one and one. So again, either one is true or the other is true or both. So this is the both case. The XOR is essentially saying that you're true when either are true, just not both, right? So 0 and 0, 0, either or, that works. But as soon as if you look at the both case, right? In other words, you're true here and you're true there, you'll be zero. So it's the same as or, except when you're looking at the both case, you're excluding the property of or that says that it can be true when both are true, right? NAND is just the inversion of AND. So you'll see the outputs of AND here. And then NAND is just an inversion of that down the line. The NOR is just the inversion of OR, right? So whatever the output of OR is, you simply have, OR 0, 1, 1, 1, NOR is 1, 0, 0, 0. The exclusive NOR is simply the inversion of NOR, right? So, or sorry, it's the inversion of XOR. So here you had 0, 1, 1, 0. Here you have 1, 0, 0, 1. Again, these are some of the logic gates. I drew them by hand just to really kind of consolidate and reaffirm what they mean. Here, we're just kind of going over how you can think of like this circuit, right, where you pass in voltage and then you have a light that shines depending on what the switches are, either they're open or off on the path. And so if they're both open, right, well, in order for electricity to flow from one side to the other, they both need to be closed. And so that kind of, if you represent the switches as A and B, It's kind of saying that A and B both need to be um, a particular value in order to be true. In other words, in order for the light to be on. So they both need to be on. In other words, they both need to be true for it to be true, for the light to be on. This is kind of just demonstrating the OR case, right? You can have electricity pass if one of them is on and the other isn't. You could have electricity pass if the other isn't and the other one is on, right? Or if they're both closed, right? In other words, but they're both on. In other words, they're both one. You could essentially still have that light function. This is just another professor who is looking at a similar idea in a different, not necessarily in a different way, but just the schematic is different. There's this idea of VDD and ground. And we generally say that, VDD is the positive side and ground is the negative side, and electricity generally flows in that particular manner. Again, this is just simply representing that idea of VDD and ground. You have a positive voltage, and then voltage is also drawn to the ground. Transistors, there's this idea of transistors and where electricity can flow from a source stopped at a particular gate, and then can then go to a particular component called the drain. And really the idea is not necessarily to get too bogged down in this idea. Schematically, though, this is kind of showing you a physical description of a gate, or sorry, a transistor rather. This is more of a schematic view, what you would otherwise see symbolically. And I don't think this is terribly important. I think what's important is thinking of transistors as being gates, or rather switches, right? So in other words, you transist electricity, right? In other words, you have electricity pass, and that can control, based on what the gate is, you can control the flow of electricity. So here in this particular case, if you pass in voltage, right? And this is what we talk about, gate voltage, right? So you pass in gate voltage G. If that's zero, in other words, there is no electricity passing through, then the gate can be considered off, because it would otherwise have to be off for electricity not to pass through. Or the gate could be thought of as closed. In other words, in order for it to be closed, that's when it means that electricity is passing through, because when it closes, there's a valid path for electricity to pass through. And so you would think that it being open is analogous, not analogous, but it means that there is no electricity passing through. There isn't a valid pipeline for that. But if it's closed, well, then there is a valid pipeline for that. And so if G is zero, we consider the unit or the switch off. And if G is one, then we consider the unit closed, right? Because it would need to be closed in order to let electricity to pass through. And so one is on, and closed means that it passes through. And so on, it means closed. So this is kind of this is a summary of that logic. But I think it's important to recognize that these kind of happen in two distinct bands. So the first is that, you have this behavior that I just described where zero is off because that means open, and that means electricity doesn't pass through. And G being one, the gate voltage being one, means that it's closed. And obviously when it's closed, it means that electricity is passing through. So it must be closed if it's one. That's one set of behavior of a particular gate. You have another type of gate which will actually function in an opposite way. And you'll see this notch here that denotes that. And again, that notch is essentially an inversion of what behavior is already established. And so if you've established the behavior of the notch, or if you've established the behavior of the gate in the way I've described, and you add that notch there, you're essentially saying that electricity won't pass when it's closed, and electricity will when it's open. And that's kind of the distinction that this professor in particular goes through, is that when the voltage is high, in other words, the voltage is on, it actually turns the gate off. In other words, it opens the switch, right? Before we were thinking about the switch being closed, and that's when electricity passes through, and that's when we say the gate is on. But here, when electricity is passed through, it actually opens the switch instead of closing it. And when the gate voltage is zero, in other words, they say that's low voltage, that tends to turn the transistor, that will actually close the transistor, right? So no longer is it the case that when you have your gate voltage as 0, the gate is off. In other words, it's open. That was before in our previous understanding of that particular type of gate. Now we're talking about another gate where the behavior is inverted. So 0 means that it's open. Sorry, 0 means that it's closed, and 1 means that it's open. And again, we have that other schematic to support that. And this is kind of the difference between PMOS and NMOS or MOSFET. I'm not entirely too sure about the specific names there. And again, this is just an aggregation of that. There was an image here that described the difference between 2 input and 1 input gates, although I think we have this image here, right? Single input versus 2 input. A single input is just you singularly have an input, and then whatever is output, that's fine. And so one example of that is in fact the NOT, right? Where you have 0 and then it inverts it to 1. You have 1 and inverts it to 0. Your inputs were singular, it's a single input. Versus a 2 input gate where you're otherwise accommodating A and B, and then you're filtering that through the particular shape, which we know to be now as OR, and then it outputs Y, which is again a particular output. And again, this is the OR gate, and so we know that OR in particular here means that you are true and either are true, and both, right? If it was an exclusive OR, that essentially means you're true and either are true, but not both. And so that's kind of the distinction there. We're kind of looking at this particular image here, and we're saying, okay, well, you have this NOT gate, right? This is kind of the whole circuit, and then here you have your transistors. Symbolically, we're thinking back to the way that we saw them before, and then you have an input of A. Now, if A, and let's kind of fill in the values here. Remember, P1 and N1 are transistors. If A is 0 and you filter that through, this is going to hit that, and it's going to hit that that transistor. And however, and again, we're thinking of transistors as switches. So I'll say switches. You'll know that they can be used synonymously, right? So A is 0. So that switch has an inversion notch before it, and so it will change it from 0 to 1, and then you'll have what you'll essentially have there is then the switch would otherwise have been off if it accommodated a value of 0, but now it's actually 1, so the switch is closed, right? So P1 here, you can imagine a line going from there to here. It's essentially saying that the switch is closed. And of course, when 0 hits N1, well, an incoming value of 0 means the switch is off, and so it stays off. In other words, it stays open. There's no electricity through it. And so if you'll notice here, this part is bridged by a particular line because that switch is closed, but this part is not bridged by a particular line because that part is open, that switch is open. And so therefore, there is a line from VDD to Y, and the output of Y would then be 1. So let me back up here. We already know that this particular switch will be closed, this particular switch will be off. But why did I just say that if there's a valid line from VDD to Y, then the value of Y is 1? The output is 1. I say that because if Y it has a path to VDD, in other words, it's being drawn to a higher voltage, then it will be 1. If this was closed and that was open, right? If the P1 switch was open and this was closed, then it's being drawn to lower voltage. In other words, the voltage output would be 0. So what I'm really trying to say is you don't necessarily say that, oh, if all your switches are open, there's no path to Y, then there is no, Y will always be 0, right? If all the switches are on, Y doesn't have a valid path, Y will always be 0. That's not the case. What we're saying here is depending on which path it's offered, right, from Y to what? Y to VDD or Y to ground? If it's Y to ground, then it's being drawn to lower voltage, and therefore it is 0. If it's Y to VDD, well, then that means that it is in fact higher voltage. It's being drawn to higher voltage, and therefore it's 1. Now let's feed in the value of 1 here, right? So you pass in 1 through A, and then you hit the inversion notch, and you hit the inversion notch that's close to P1, and then your value is inverted. So 0 for P1 actually means the switch for P1 is open, right? 0, a gate voltage of 0 means the switch is open, means there's no electricity being conducted. If we are sticking with the band of switches that we know that behaved in this way. But then, of course, you have one being sent to N1. And so the N1 switch is closed. And therefore, you have a valid path from Y to ground. And so the value is 0. So if the path it exists from Y to ground, the value will be 0. If the path exists from Y to VDD, then the value will be 1. And again, this is just sort of an explanation of that. And I think this distinction is important in the sense that you need to know whether it's going to VDD, then it'll be 1, which is easy to remember because high voltage, higher number, it's 1. Low voltage, lower number, it's 0. Again, we've looked at more logic gates. And again, I think this is just rehashing information we know. The XOR is an exclusive OR. Usually you'll see the OR bounded together, the inputs in OR bounded together by addition. And you'll see that if you're looking at XNOR, you'll have sort of a line above that addition to denote that it's in fact XNOR. NAND is essentially not AND, right? So you'll have AND, which is usually bounded together by multiplication. And this is true across several subjects. When you think of things that are ANDed together, they're multiplied, or when they're ORed rather than they're added. And so again, if we look at XOR, that means it's an exclusive OR, which means that it's either or, but not both. And the truth values reflect that. NAND is, it is essentially all of the values of AND, except it's negated, right? You can think of that additional N on the front of AND as a prefix being a negation of all the values that you know to be true for AND. And the NOR is essentially just OR again, negated if we're utilizing that idea of it being a prefix. And then, of course, XNOR is simply taking NOR and inverting its values. So this is interesting, right? You end up filling in the values here, and it's kind of tedious, but I'll walk through it very quickly. P1, right? So if they're both 0 here, well, then you end up sending 0 to P2, but it gets inverted, so this is closed, right? So this is closed, so you have a valid output to Y. B gets sent to N1, not a big deal, right? So B gets sent, which is 0, so that's open. A is 0, right? So N1 again is open, right? These are both off, N1 and N2. A gets sent to 0, B gets sent to, A sends 0 and B sends 0, and N1 and N2 are both open. So we already know that we're not going to ground. And in other words, the output Y will not be 0. But what happens in the path of A is it gets intercepted by P1. And it also gets sent to P2, right? And they're both inverted. So if P2 and P1 are both accepting 0 and they get inverted, they essentially become 1. So P1 and P2 are both closed. In other words, they're on. In other words, they conduct. And so there's a valid path from Y to VDD. In other words, the output is being pushed to a higher voltage. In other words, the value for Y is 1. And you can kind of do this for each particular case. I'll save us the trouble. This is kind of just showing the 1-1 case, right? So you pass in 1, and what happens is that, you know, N2 is now on and N1 is now on, and on is, in other words, closed. In other words, it conducts. But because of these inversions here, P2 is open, P1 is open, right? Because those are actually accepting values of 0, because when you filter in 1 as a value to each of them, you actually invert them to 0. And so you actually have them as on, we know, or off rather. We know when the gate voltage is 0, that means that the switch is on, is off, right? It's open. We're looking at a circuit here, and we're asked, well, what's the output of the circuit? And so we're looking at really a combination. We're looking at a graph that is in some sense, in an actual sense, really a combination of multiple types of logical gates. And you'll see how if you flow in values through these prongs, they will be filtered in through these logical shapes, if you want to call it, but they're really gates that will then dictate what the final output is, right? So if I filter in 0 for A, B, and C, right? What's Q? What's the output? This is our equivalent of Y. A gets filtered in B gets filtered in, they're both bound by the AND gate. We know that if something is 0 and 0 and they're bound by AND, the output of that is 0, right? So 0 is being fed here. B and C are both 0, and they're being filtered through the OR gate. And we know that when you're talking about OR, you're essentially saying that when either or are true or both, you'll get a value of 1. But in this case, they're both 0. And so you have a 0 from here too. And you have a 0 from here too, because if you filter in B, which is 0, and C, which is 0, well, they're all going to send in values of 0. So we know that 0, 0 for AND is 0, 0, 0 for OR is 0, and 0, 0 for another AND is 0. And so naturally, you'll have 0 here and 0 here. Again, filtered through yet another AND, and then it will be filtered into 0. This will be 0. And so we essentially have nothing for that. This is the 0, 1 case, right? So the 0, 1 case, if they're filtered through the AND gate, says, hey, if I'm an AND gate, you need to be true across both cases, or it's not happening. I'm not going to give you a value of 1. AND is specifically true for both or false in every other case. So we get a 0 here. The OR actually says, okay, well, I know what OR, either if you're 1 in either case or both, I'll accept you. And so you end up being 1 here. And then the same can be said for this one here, where 0 and 1 as accepted values. Well, C is 1, right? So C and B are 1, which means we're actually talking about this particular case. So C and B are 1, and is happy. It sends off a 1 through the other side. We had A being 0, B being 1. That's a 0. This is a 1 and this is a 1. And then this AND is happy because it accepts a 1 and 1 from here. We know that 1 and 1 is 1. And then it sends a 1 here. It sends a 0 here. Ultimately, that's an OR gate. And it says, I just accepted a value of 1. I don't care through how many gates it was filtered. The final output from those gates was 1. I'm accepting a value of 1 and a 0 from the other side. We're bound by an OR gate. And so we're going to output the value of 1 or 0, which is 1, right? Either or both. Again, this is more of talking about sort of the equation representation, right? If you think of this gate in here as particularly as W, well, A and B being sent in is actually A times B. The OR is plus. And again, you have another BC here, B times C, if you want to think of it that way. And then Z is essentially saying, okay, well, that's X times Y, right? So this is X times Y. In other words, whatever the value of this is and whatever the value of this is, multiply it. And you can even think of this in terms of actually, I won't go there. I don't want to confuse you here. It's enough to know the symbolic analysis without the equations, I believe. And so I wouldn't want you to get confused. This question's interesting. So you kind of just look at this particular circuit, and what you do is you say, okay, I have what's in this circuit, right? What are some of the core features of the circuit? The core feature of the circuit is you have an A and a B, right? You have an A, you have a B, and you have an output. So what you can do is you can actually create a truth table, right? Pass in 0, 0 as A and B. What's your output? Pass in 0, 1 as A and B. What's your output? Pass in 1 and 1 as A and B. What's your output? So you have 4 combinations, right? 0, 0, 0, 1, 1, 0, 0, 1, 1. What are the truth values? And then based on that, try to match it to what you know about, well, which one does this resonate with? Is it the AND truth table? Is it the XOR? Is it the NAND? Is it the, And so if you do this, you'll find that this is the table that you arrive at. 0, 0, 0, 0, 1 is 0, 1, 0, 0, 1, 1 is 1. So what it ends up doing is it ends up saying that you're only true when both are true. Which logical gate do you think that is the case for? It's obviously the AND. So this is, in fact, the AND. This is lecture 2. There were some conversions here. And the conversions were essentially that just some basic stuff. So if you want to convert a number from decimal to binary, right? You want to convert a number from decimal to binary, something in base 10 to something in base 2. What you end up doing is you end up mapping out, at the top at least, from left to right, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so forth, right? And you particularly add you particularly put the equivalent of those numbers underneath, right? So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, and so on. And then you tally, well, not really tally, but you put a 1 under the thing you would need that would contribute to the addition of the number you want. So if I'm looking at 45, well, I need 132, I need 1 8, 1 4, and 1 2, and 1 1 rather. That's all I'd need to create 32. And again, you can only use ones and zeros, so you don't want to put a 2 here at any particular time. And so that's what you end up doing. And so this is your final answer. 101101 is in fact the decimal equivalent. That is the binary equivalent of 45 in base 10. If you wanted to go the other way around, I haven't really wrote this here, but if you wanted to go the other way around, what would you do? You'd simply put 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5 above this binary number. And of course, what they represent, right? If 2 to the 2 is 4, 2 to the X is something, right? You put those numbers there, and then you're like, okay, well, what number did I need to add in order to get 45, right? Or what number did I need? What numbers do I need to add in order to get that in order to get any particular number? You don't know what decimal number it is yet, right? You just have 101101 at your disposal. You don't know what number, what decimal number, what whole number that will come out to be. So what you're doing is you're saying, okay, well, I know that each of these binary numbers represents a place. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And after I have those values, I know that I had to have put a tally underneath a number that was part of my addition. So I'm going to take everything that has a 1 associated with it and add it up. And then the final product that you get from that, I don't want to say product, that would make you think it's multiplication, but the final sum that you get from that, you would think, is in fact the number that got you to that binary number in the first place. Right. So here in this particular case, I have 132 base 10. I want to represent 5. You want to represent that in base 5. Well, then see, the thing is, when you had a decimal number in base 10 and you wanted to go to binary, you're actually saying, I want to take a decimal number, which is represented in base 10, and now I want to represent it in base 2. Base 2 is binary. That's why you converted from, that's why you were using 2 as your superscript here, right? That's why 2 was our superscript. Here, when you're converting from base 10 to base 5, the 5s will be your superscript. So that's conversion from decimal to binary, binary to decimal. Now let's look at adding binary numbers. So first, a very simple case without carry. You have a bunch of binary, you have one binary string here with a bunch of bits, as they call them. Singularly, they're known as bits. Collectively, in a group of 4, if you have 4 bits together, that's known as a nibble. If you have 8 of them, that's known as a byte. So here in particular, right, 1 0 is 1, 0 1 is 1, 1 0 is 1. So you're kind of just flip-flopping between, very easy addition. There's no carries. So how do you deal with it when there's a carry? So 1 1, what do you do? Put a 0 down, carry 1. That's the goal, right? So I have 1 1 here, put a 0 down, carry a 1. Now I have 1 1 again. Oh, sorry, I don't have 1 1. It's just 1 and 0 0. It's just 1. And then we're back to normal. So this is kind of a special case, right? So you have 1 1, 0, put a 1. You have 3 1s. Put a 1 and then put another 1. So if you have 3 1s together, put a 1 right at the top. Sorry, if you have 3 1s, put a 1, but instead of, sorry, put a 0. Okay, I'll back up for a second. If you have 2 1s, what you do end up doing is you put a 0, you carry a 1. If you have 3 1s, you put a 1 there and you carry a 1. That's essentially the idea. So you did that, right? So 0 and 1, because you had 2 1s. Now you have 3 1s. Put a 1 and put another 1. You have 2 1s again. 0, 1. You have 2 1s again. 0 and 1. And then you just have 1. Again, we're asked to convert 1010 to its binary equivalent. Again, I know that this is binary, and so I know that the superscript must have been a collection of 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And then I'm going to essentially go through and find out what the equivalents are for 2 to the 0, 2 to the 2, 2 to the 3, 2 to the 4, or whatever, or however many binary numbers bits there are rather. And then I know that everything that needed to be a part of the addition of the number I want, the whole number I want, the decimal number I want, must have had a tally underneath it. And so everything that has a tally associated with it, in other words, a 1 as part of that binary string, I will in fact just include in the addition. So if there's a 1 underneath 2 to the 2, that's going a part of my addition. Everything with a 0 was not a part of my addition, so screw it. So in this particular case, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 4, or 2 to the 3 rather. Well, this 8 was a part of my addition, so I'm going to do 8. This was part of my addition, so I'll do 2. And then, so I guess my number is 10. Again, so you go through, you create the truth table, and then you essentially get the logical gate. Sorry about that. Anyway, so we have, so, again, you don't necessarily need any one of them in particular, in the sense that you don't need both of them attached at the same time, right? So you don't need the circuit to know that it's, you don't need the NAND truth table or the NAND symbol to know that it's a NAND, right? Because you can form this truth table yourself. You can pass in values and you can judge for yourself what this truth table will be. When you arrive at this truth table, you'll see, 1, 1, 1, 0. That seems like the inversion of the AND values, right? So knowing the truth tables is important. And again, this is just kind of going through filtering values through the gates. That's very essential. And so I think symbolically, this is important that when you look at a NAND gate, you're actually looking at A and B being filtered through and then an output Y. So this is kind of showing you that these circuits are kind of embedded in these logical gates, and this is what's happening under the hood. So when you get A and B, and then you have this big word "and" on that logical gate, what's actually happening underneath there? What does that filtration process look like? And this is kind of what that looks like. Write an equation for the circuit, right? So you have A and B, right? And we know that A and B are bonded together under the multiplication, right? So you have A times B. That's going to fit in somewhere. We don't know where yet. We'll get some structure soon. You have B or C, right? Because B or C are being filtered through here. And you have C and what seems to be B, right? So C and B, B or C, A and B. So it seems like A and B is standalone, right? A and B, if one A and B, that's standalone, that's going straight to OR. We know that things that are ORed are added, right? So eventually the dominant operation here that's going to connect all this together is the OR. On one hand, you'll have A and B. On the other hand, you'll have this larger bracket where B or C and B and C are being bounded together by an AND, right? That's kind of how that color code looks. So you can actually express a circuit as an equation, right? This seems to be like the problem repeated again. And then again, you're just going through that. So that was kind of the sort of a higher level understanding so far. Here, we're kind of looking at the idea of building an adder from a high level at least, right? You have sort of this box where 2 inputs are filtered in, n bits wide. The notation for that is you have the prong and you do a dash. That'll tell you how many bits wide it is. So A and B accept binary numbers n bits wide, right? So you have n bits wide, and then ultimately you would expect the output to be A plus B. It seems like we get back into a conversion a bit. We go into hex as sort of a digression so that we can then better understand that idea. But as far as hex is concerned, that's actually a different part. So we're doing more conversions. That's fine. Okay, and then we're looking. Okay, so this is kind of where it really starts, right? So you're building a machine that's essentially an adder. It's a 4-bit adder. There's a detailed description here of what that 4-bit adder is. Ideally, you think of these as being switches. You turn the switches on and off, and on the other end, a light will turn on based on what the addition is, right? So if you're adding a 4-bit number with a 4-bit number, A will have 4 prongs to represent whether or not to represent those bits. B will have 4 prongs to represent those bits. If A, and so if the switch is on, it's 0. If the switch is closed, it's 1, right? So if this switch was 1 and this was 0 and this was 1 and this was 0, you'd expect closed, on. And then again, same here, closed, on, closed to represent whatever number that is, right? And where on is 1, off is open, off is 0 rather. Then on the other end, as soon as you do that process, right, you switch everything on and off, a binary sum will be represented because if you add 4 numbers together, sorry, you add 2 binary numbers, each 4 bits wide, together, you'll have an answer that's 4 bits, right? And so that's why there's 4 prongs here. But you'll notice an additional prong that's for the carry, right? Because sometimes in binary addition, we actually have a carry. And so if you're adding, let's say 4 and 3, well, okay, let's first convert 4 to its binary equivalent. Let's convert 3 to its binary equivalent, which we've covered. And then A1, A2, A3, A4 will represent, let's say, the binary equivalent of 4, A1, A5, A3, A6, A7 represents the binary equivalent of 3. You add them together, and then you'd get an output. And so that output would be S0, S1, S2, S3, and then whether or not a carry is applicable. And you'll see that a carry is in fact, well, not in this, well, yeah. So a carry is in fact applicable when you do 7 to 9, in which case you'll see that a carry is needed, right? Because you do 1, 1, 0, 1, 1, 1 again, 0, 1. Because when you hit 1, 1, you put a 0, you carry a 1. So 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1 again. And then your final digit as far as the sum is concerned is 0 here, and you carry a 1. That's the problem. Because I haven't yet represented the sum as it truly is. I've represented the sum as to whatever I could fit. And so you kind of introduce this idea of a half adder where, again, you have a high level machine where you take in 2 bits and you produce a sum. And then whether or not there's a carry, there's an additional carry prong. So the idea is that A and B are 0 and 0, and then the sum is 0, sure. Again, same as we'd expect, 1 and 0, 1, 0, 1, 1. The carries are still 0 for each of these. I didn't need to do a carry. As soon as I hit 1 and 1, well, then that's when the carry comes into play, right? So that carry becomes 1. And this is kind of the circuit representation of that idea. You'll see that if I were to apply the exclusive OR operation to everything that I add, the sum, the S1 column, comes to fruition in the way I want. So if I say 0 and 0 is an OR, let's say they're bounded by an XOR rather, exclusive OR, in other words, they can only be true when both are true. Well, then this would be 0. And here they're not both true. They can only be true. Sorry. Exclusive OR is you're true in either or, just not both. So here you're not true, so you're 0. Here you're not true when they're both true, but you are with either or. That's what exclusive OR means. And so you get a 1 here, then a 1 here as well, right? Because you're either or, just not both. And so when you look at both, you're like, what's going on? You get a 0 for the sum, which is what you'd expect, and then you want to carry 1, right? So we know that everything we need to add is perfectly bound together by an exclusive OR. If they're bound together by an exclusive OR, then we get that table that we want, right? A and B, if they're bounded by an exclusive OR, will give us the sum we expect on the table we expect for the sum at least. What about the carry, right? Well, if you apply the AND operation to the carry, then you'll get what you expect, right? So 0, 0 won't have a carry, 0. 1, 0 won't have a carry, 0. Because again, we know with AND both have to be true. 0 and 1 won't have a carry, so it's 0. But 1, 1 turns out to be 1. So this is kind of the circuit representation. Pushing A and B through the AND will give you the carry, whatever that is. Pushing A and B to an exclusive OR will give you the sum, whatever that is. So this circuit gives us the table we want every time we want it. It's a half adder. You'll notice a full adder is different in that it actually takes into account the addition from the previous computation, right? It has a carry in. So it's actually factoring in what was carried out from the previous. They're bounded together by exclusive ORs, that is the sum. And then the sum is computed this way, right? A, B, and then whatever the sum of A, B is, you exclusive OR that with C, and then that is in effect what you get for your sum for each of these, right? So A and B, and then of course the carry as well. So if you do an exclusive OR on all of these, and how you do an exclusive OR on all of these is you first consider two, right? A and B. You're like, okay, well, what's the exclusive OR of that? Then take that number, whatever you get, and then calculate what the exclusive OR would be with that C in. And you'll see that the sum will always be what we expect it to be, like 0, 0, 0, 0, 0, 0, 1 is 1, 0, 1, 0 is 1. So it's always what we expect it to be if they're bound by this exclusive OR. In other words, we compute A and B under the exclusive OR binding, and then we calculate whatever we get from that exclusive OR binding with another exclusive OR, and then we'll output what we want as the sum, and it makes sense to us. Right. So that's the exclusive OR, and then we kind of just take for granted that the C out is, whatever this happens to be, which is not entirely too straight to the point. There's a much deeper explanation for that. So this is kind of the full adder circuit. You can see that I said that A and B should be bound under the exclusive OR, and so that's actually what's happening. They're being fed into an exclusive OR, and um, and the C in is also being bound by the OR of that, right? Because remember I said that first you compute A and B. So first just feed the exclusive OR of A and B into the OR gate, right? Which we've done here. But then take the C in and also compute the exclusive OR between the result of the exclusive OR of A and B and C in. So you actually need a completely other gate in order to do this, right? Because you're doing A and B first, then you do C in. So first you compute A and B's XOR, then you do C in, the result of that, and C in, then another XOR. That will always breed the sum. And so that's actually why you have two XOR gates here in the full adder circuit. Now, if you do C in order to really account for this here, right, A and B has to be multiplied. So you know that you'll have interceptors here. Well, they will intercept and multiply. And then whatever the result of that is, you'll have A coming in, right, which you do. You'll have B coming in. But then you'll also have A, so AC in, right? So right, so the output, so there should be something connecting A and C to an AND gate, right? Which is where this particular portion comes in, A and C to the AND gate. And then B and C in, right? So B and C in as well. So they're all kind of bound by that AND gate. And eventually you'll get your C out value. Well, these should actually be ORed together, XORed together, in fact. Or not XORed, rather, just ORed, right? So your AB component, your AC component, your BC component are all ORed, and that's your C out. It says that it's been rewritten to reduce the number of gates needed. So depending on what that means, here's what's known as a ripple carry adder. So if you're curious about what do you do when that carry is always in excess, you have A and B, and then the sum is produced by adding them, and then that carry is then sent off as a input to the next one, and then you end up computing, and then the sum, and then you keep doing this for several such half adders. So it says here that you're actually depicting a ripple carry adder. adds two multi-bit binary numbers. First stage, you have a half adder for the least significant bit, right? So when you think of bits in the way that they're organized, you can notate them underneath as being A0, A1, A2, A3, A4, and you produce a sum. So that this first one is taking in A0 being just one bit of A1, A2, A3, right? So you have 4 bits, A0, A1, A2, A3. So this is specifically, in other words, I think probably the way I want to tell you this, or the best way I want to tell you this is, right? So when you're looking at them stacked, right, in this column-wise fashion, this is your A0, this is your B0, right? So your A0 and B0 are being filtered in through this half adder, and then a sum is being produced that put underneath. Then whatever that carry is, right, if there is a carry, in this case there is, you go to the next column, right? So you're taking that carry into account. And then again, B1, A1. So what's B1, A1? This is A1, this is B1, this is A1, this is A2, this is B2, this is A3, this is B3. So that's the understanding of A0, B0, so on and so forth. And the carry outs are processed, right? You get a carry out as well. So you propagate carry outs. This is a ripple carry adder in the circuit format. Again, you can see that these are half adders in the way that they're depicted, as we said before. Right. So you've taken in many full adders. The first of the gates, or the first of the circuits, in other words, this top portion here, is in fact a half adder, because you don't need to process a carry in for the first addition. There is no carry in for the first addition, right? When you're looking at that first column, 1, 1, 0, 1, right? When you look at 1, 1, there is no carry coming in. So you only need a half adder for that, right? A half adder will characteristically only accept two inputs and then output a carry. You don't need a carry in from a previous addition, right? So you can just tack on a half adder and then multiple full adders so that they can then propagate those carries. And again, this is just a demonstration of that, right? So you have your 1 and 1, and then you have a half adder, and then the carry comes through, right? But a good question here might be, okay, so this is not actually adding two binary numbers, or yeah, two binary strings. This is more like this is an incrementer, right? So what you do for the incrementer is you set in a default. So the first A and B prongs for the first half adder are just 1 and whatever number happens to be. So you have 1, 0s, 1, 1. That's what I want to increment. I'm denoting this one here as A0, this one here is A1, this one here is A2, this one here is A3. And you put in a 1, right, by default, because you want the number to be incremented. And then this is just what your A0 was. And they're both put into a half adder. You output a sum. So if you were adding 1, 1 in column-wise format, you would actually do 1, 1, right? So you have 1, 1, and you do a 0 and 1. So your carry would in fact be 1. So you feed that carry into another half adder. That becomes an A and your B now, right? But that B is the next number in line. And so you're actually doing 1 plus 1 again. Again, you have a carry of, you have sum of 0 carries 1. You do that again. Here you're just doing 1 and 0. The sum is 1. Your carry is 0, right? And then in this case, you're just doing 1 and 0 again, your carries. So this is a ripple carry adder. You're rippling the carries through the sequences of adders, even though one of the carries, even though at times the carry can be 0, you still treat that as a carry in this ripple system. This one says, well, you have a ripple carry adder, and again, we abstracted away these circuits for the ripple carry, or for the half adders. We have many half adders attached together. We abstracted away each half adder by just putting a box here and saying, this is your X0, this is your 1, these are your inputs, A and B, right? So you actually have four adders that are attached together. This is saying instead of incrementing it by one, can we in fact increment it by two? There's some otherwise what I think to be a convoluted explanation as to how you actually abstract away this one here. You take away this as part of the sequence of gates, and somehow that works. I'll have to look in a little bit into why that's the case. We go sort of an annotation there for my own sake, but what's hexadecimal? What's hexadecimal to binary? I'll explain this very shortly. Hexadecimal numbers are ways to actually make the process of writing binary numbers easier. So when you have, let's say you have an 8-bit, right? In other words, bit as in being a singular digit as part of a larger binary string. So like 1, 0, 1, 1, 1, 1 is a bit, 0 is a bit, 1 is a bit. Those are all bits. And so a group of 4 is a nibble, right? A group of 4 bits is a nibble. So what you can do is you can create this whole other different paradigm called the hexadecimal system. And you can say, okay, well, as part of this hexadecimal system, 0 through 9 will be 0 through 9. In other words, if I want to write 9 in hex, that will simply just be 9. If I want to write 8 in hex, that'll simply be not. It will simply be 8. So 0 through 9 in a real sense is in fact what you would expect to be, which is just the number itself. As soon as you hit 10, you start saying, okay, well, now I've hit 10. Now I'm going to introduce letters, right? So 10 is A, 11 is B, 13 is C, and so on and so forth through. And so what you end up doing is you say, okay, well, let me look at a very large binary string. Let me group them into nibbles, in other words, groups of 4. So you have 1, 0, 1, 1, 1, 0, 1, 1. I'll just take one of those, and that's a group of 4. 1, 0, 1, 1 would be a nibble, and you would then say, okay, well, this will be one hex digit. So when you have a hexadecimal number, you'll see them like, 2, 3, F. Each hexadecimal digit there, the 2, the 3, and the F, has in fact 4 binary bits as part of each hexadecimal digit. And so 2, 3, F, 2, if 2 will be extracted to a binary number. Sorry, yeah. 2 will be extracted to a 4-bit binary number. 3 will be extracted to a 4-bit binary number, and F will be extracted to a 4-bit binary number. So 3 hexadecimal digits, 4 bits each, 12-bit binary number that is encoded in it. So what you do is you say, okay, well, my first hexadecimal digit in 23F is just 2. Let's find the decimal equivalent of 2. That's your binary number for that part. Let's move on to F. Let's move on to 3. What's the decimal equivalent of 3? That'll be a 4-digit binary number, 4-bit binary number. What about F? Well, we know that F isn't necessarily a number. We have to track this down to the scale that we know, where 10 is A, B is 11, C is 12, and then D is 13, and then 14 is E, and 15 is F. So 15 is F, right? So now I have to take 15 and convert it into binary, right? So that's how you string together your binary numbers, right? And then you have that set of 4 that you got from the first digit, another set of 4 you got from the second digit, and another set of 4.